Okay, thank you, Josep, for the introduction, and also Mark for organizing these webinars and for inviting me here. It's a pleasure to be here between former colleagues and friends. So thank you very much. Here, as Josep mentioned it, we are talking about remote sensing monitoring, especially InSAR, and then we'll give some insights of what we are doing also with multispectral analysis of optical images. Here we can see the contents. We'll give a brief introduction about who we are, DARES, some InSAR basics, from the very basics of SAR images till the examples, what we can get, and then how we mix our results with multispectral analysis of optical images, and we will end up with some final comments. So, as Josep mentioned, I joined DARES in 2019, and we're a company, DARES Technology, that we are offering remote sensing services, mostly InSAR, that we will see what it is and what we can get. And basically, we are working with radar images, and we don't need any kind of installation in the field where we are working. And with these radar images, with some treatment, we can get ground displacement with a millimetric precision. And with this, what we are doing mostly is trying to prevent events that could happen in different facilities or companies we are working for. In DARES, we are a group of geotechnical engineers, geomatic engineers, telecommunication engineers, mathematicians, and other stuff. And we are in Barcelona, actually in Castelldefels, and we are also working in Turkey, Australia, all over the world, and we have an office in Santiago de Chile. Okay, just to go into the topics, some basics about the remote sensing. As I said before, remote sensing is about getting data without being in contact with, in this case, with the Earth surface. And for this, we have two kind of sensors. We have what we call passive sensors. These sensors need an external source of energy to work, to acquire data. And then we have active sensors on the other hand. And these active sensors, they produce their own energy to acquire data. Okay, one example of active sensor are radar sensors. They produce their own energy, so they can measure, they can get data during day, night, and due to the wavelength that they are working, they can also get data even if we have clouds. Okay. Radar sensors, they work with the distances, so they have what we call side-looking geometry. Let's say they are not looking on the vertical, but they are looking with a certain inclination on one side. So this is because if we have this side-looking geometry, the probability of having points at different distances from the radar increase. And since we are working with distances, we have this side-looking geometry, okay? And the images, what we are working with is with amplitude and phase. What images provide you with is amplitude and phase. Optical sensors, which are passive sensors, they need an external source of energy, for example, the sun. So it means that they cannot work during the night. And due to the wavelength, some of these sensors cannot work if we have, for example, cloud coverage. And these sensors are not looking in side-looking geometry, but in nadir, on the vertical, because it's not about displacement, but reflectivity. Okay. Here we have an example of a radar image and an optical image, since we are looking in...
Nell'informe di medicina, se si può filmare in Natale.
Since we are looking not in nadir, but from side looking, the image is distortionated, and in the optical image is the typical image that we get. And what we have here is the radar satellite, actually the one we are working with the most, which is orbiting at 700 kilometers. This is the flight direction. This is the antenna used to acquire the radar images. And this is what we call incidence angle. As I mentioned, we are not looking on nadir, just on the vertical, but with a certain inclinations to get more points which are at different distances. Okay, so regarding the SAR sensors or the SAR satellites, there are different sensors. For example, the one we are working the most is Sentinel-1, and each of these have different features, okay, which are the wavelength, the frequency at which they are working, the spatial resolution, and also the revisiting time. This is important because it means that you can get one image each 12 days. For example, with Sentinel or with TerraSAR, you can get one image with each 11 days. So if you want more frequency of images, if you want more data, you need to take images from satellite that have a lower revisiting time. But not only this, also the frequency is important because it gives you a clue about the penetration capability. So for satellites, for example, TerraSAR that are working at lower wavelengths, so at higher frequency, the penetration capacity is lower than for satellites, for example, Sentinel, which are working with higher wavelengths, so lower frequencies. So if you have a vegetated area, the capacity of penetration of the pools working with X-band satellites will be lower than the capacity of penetration that can have the C-band satellite. Okay. So we work with radar images. Actually, in InSAR, we work with synthetic aperture radar images. These are radar images that what they are doing is taking advantage of the movement of the satellite because it's orbiting the Earth to simulate a larger antenna and to increase the spatial resolution. This is what we call synthetic aperture radar. And as I mentioned before, we are looking on nadir, but like the optical sensors, but inside looking geometry, because in this way we increase the probability of having points at different distance. Okay, and this is why we get distortionated images. So this would be a SAR image of a volcano. We'll see it later. So we cannot, when we talk about radar images, we cannot think about optical images because, yeah, you can differentiate sometimes the scene, but they are different. They are basically distortionated because of this effect of looking at side-looking geometry. The satellites are orbiting the Earth in a quasi-polar orbit. It means that they are going from south to north, then from south again, and they are looking, as I said before, on its right side. Okay, so it means that when it's going from south to north, the satellite, it's looking to the east, and when it arrives to the north and hits again the south, it is looking to the west. Okay, you will see it better here. when we are talking about ascending orbit, here we have the Mount Etna, we have the satellite coming from the south and going to the north, and the satellite is looking to the east, okay? When the satellite is going from north to south in the ascending orbit, is looking to the west, okay? And this is the optical image. The radar image we could get in ascending mode of the Mount Etna is this one, and the radar image that we can get in the ascending orbit, of the Mount Etna is this one, okay? So what's SAR interferometry, right? So InSAR is interferometric synthetic aperture radar. Now we know what's a synthetic aperture radar image, is a radar image. So what's SAR interferometry? So SAR interferometry is using the phase of the SAR image. When we have a radar image, a synthetic aperture radar image, for each pixel, we have two types of data. We have the amplitude of the backscattering. I send the signal to the Earth, and the signal is coming back to the satellite. So if the backscattering is good, I will receive a good intensity. I will have a good amplitude. Okay. And the second data I have in the radar image is the phase. And the phase is related with the distance from the satellite to the ground surface. And this part of the SAR image, the phase, is what we are using to calculate the ground displacement doing interferometry. You can tell me, yeah, Guillem, here we can maybe identify something. But here in the phase, I mean, it's kind of random numbers. Yeah. The point is that when we do interferometry, we compare the phase of a SAR image at time 1. We launch our pulse, it backscatters, it comes back, we receive amplitude and phase, we get rid of the amplitude, and we take the phase. Okay? If we are working, for example, with a Sentinel-1 satellite, we will have another image of the same area. For example, if we are in Europe, after 12 days. So I will get the SAR image after 12 days. I will get rid of the amplitude. I will take the phase, and then I will subtract both phase images, which has a difference of 12 days. Okay? If I have a difference in the position of if the asset, the area, what I was monitoring, what I was having in the first image, it has changed the position, I will have a shift in the phase. The phase of the first image is this one, R1, and the phase of the second image is this one. So I will have a shift in the phase, and this is the displacement that I can get. How much is this displacement? So this displacement goes from pi to minus pi, so 2 pi, so 360 degrees. But yeah, okay, very good. How much is this in centimeters or in meters or in kilometers? It's half of the wavelength. So if I'm working with a Sentinel-1 C-band satellite that it's operating in a wavelength of 5.6 centimeters, this distance means 2.6 centimeters. It means that one cycle from red to blue, so from red to blue, these are 2.8 centimeters. I have had a displacement of 2.8 centimeters. Okay, and there's one thing important here, that is the direction of the displacement. So what I'm measuring is the distance of a given asset or surface in the earth, wherever, from the satellite in the direction of the beam of the electromagnetic pulse. And this is what we call line of sight. So the displacements that I'm getting are always according to the line of sight of the satellite. Okay, if I have these houses moving horizontally and they are not moving towards the satellite or against the satellite, I will not see it. My maximum sensitivity will be when my asset, my ground surface, pixel, whatever, is moving in the line of sight. Okay? But what's happening here? Not everything we see directly in the interferometric phase is displacement. Why? Because the phase is sensible to the topography, to the displacement, and there are some artifacts due to the atmosphere. Remember that the satellite is orbiting at around 700 kilometers. We can take images through the atmosphere, but that's not for free, let's say. And there are some artifacts, especially during the day, due to a temperature. So these fringes that we are getting here, okay, that we said, okay, if we are working with a Sentinel-1 C-band satellite, from this red to this red, there are 2.8 centimeters of displacement. This is, for the ones that are not familiar with this, it could be something like a topographic map, right? You know the contour lines, and you know what's the difference between a contour line. So the closer the contour lines, the steeper the terrain is. Okay, but here these fringes are not only related with displacement, but they also have artifacts to the atmosphere. And here there is also topography, and there's the curvature of the Earth. And I need to filter all these things. For example, here there's an example. This is in Lombok, in Indonesia. Here there was an earthquake. So without knowing anything, you can expect that the magnitude, not the magnitude, sorry, the epicenter of the earthquake could be somewhere like where the fringes are closer one each other, because here is where we have the larger displacement. And remember, this means that from red to blue, if we are working with Sentinel-1, we have 2.8 centimeters. And here we have what we call the correlation, that fringes are getting closer and closer because we have larger displacement, and at a certain point, of course, what we say the correlation is that we are not able to measure the displacement in these areas because we are getting displacement larger than half the wavelength. And here, sorry, this is what we call rapid phase. Just after it's here. This is the wrap phase, and if we unwrap the phase, so we can get the real displacement. This one. So just what we have been saying so far, we have two images, the phase of two SAR images. We compare this the phase, we get the interferogram. Here we have topography, displacement, atmospheric artifacts. We calculate the topography, and we remove the topography, and we get this interferogram where we can see some spots. But from here, we need to get rid of the atmospheric artifacts, because we will have reliable points that are the ones in which we are interested. We will have topographic residue, which has not been eliminated during the topographic correction. And also we have the atmospheric phase screen that we need to delete. How can we do this? So here is where we talk about persistent scattering interferometry, in which we are not using just two images, but we are using a bunch of images, of SAR images. In this way, we can generate, we can create a model of displacement over time, and we can remove these topographic artifacts that we still had, and also this atmospheric noise that we had there. So with this bunch of images, which usually are a minimum of 20 images, we can create a model of displacement, increase the accuracy of our measurements, and just take and get rid of the other parts of the fringes of the face, and just left the displacement. Here we have some examples of InSAR analysis. This is the city of Jakarta, and we can get, here we got the displacements over the city. Green points are, this is in line of sight, remember. It means that green points are more or less stable. Yellowish, reddish points are moving away from the satellite. So we would say that here we have subsidence, here we have more subsidence. I guess you know, for example, in Jakarta, they have a lot of problems with underground water. So this is producing subsidence. And the bluish points are moving towards the satellite. They are going in the direction of the satellite. Why? Who knows? So, and also InSAR, one of the main benefits is that can give you a full picture of what's happening at large scales. These are 5 kilometers. So this is a huge area. You also can work at smaller scales. This is the line 9 in Barcelona. And again, here we have displacement. This is the rate, centimeters per year. And again, green is more or less stable. And the reddish points are moving away from the satellite. So someone would expect subsidence. And blues are going towards the satellite. So here we are reducing the scale, and we would be working at small scale. And not only you get velocities of displacement, you also, since we are using a stack of images, you are getting the spatial evolution of a given point, or the spatio-temporal evolution of an area. And then from here you can start playing with time series, with InSAR, and with the evolution of displacement in the terrain, and identifying trends. Like, for example, here we could see this is a time, this is displacement. We could see that, for example, a given point here was suffering displacement. It was like experiencing subsidence. And here, between November 2017 and January 2018, there was an increase in the velocity of displacement. And this is why I say that from here, you can start playing with data coming from InSAR. For example, here in DARES, one thing that we do is analyze these areas that are experiencing an increase of velocity of displacement, right? For example, here we have another time series. This is time, this is displacement, and this is the information for a given point. How this point, how the displacement of this point is evolving over time. We saw that there was a velocity of displacement, a constant velocity of displacement for a given point, and at a certain time, this is the info you have for a given image. So if we are working for Sentinel-2, we got one image at a certain time. After 12 days, we got another image. After 24 days, 12 days between this and this, we got another image, 12 days more, 12 days more. So we saw that here there was an increase of velocity. So here there was a constant velocity of displacement, and here increased, and it remained constant. This is what we call trend change indicator, if the velocity is increasing or decreasing at a certain time. Or also you can detect areas where the velocity is accelerating. It means that you had no displacement or a constant velocity of displacement, and at a certain point the velocity increased, then increased even more, so this area is accelerating. Okay, and this is what you can see for different points you have in your analysis. So in these cases, you can say, okay, this is accelerating. What's going to happen? So you can easily perform an InSAR velocity analysis, in which this is a very first approach. Of course, here we are not considering geotechnical parameters, like if you were in peak conditions regarding the friction angle, and now you are in residual conditions, residual friction angle, you had cohesion, now you don't have cohesion. We don't take into account thermal effects, like maybe maybe they could even accelerate more the displacement you are observing. What we are doing here is just assuming that if we have an acceleration, if we have a velocity of displacement, this velocity of displacement will increase following the same trend. So what we are getting here is when this velocity of displacement will be infinite, or if we get the inverse of the velocity, when this velocity will be zero. So when the acceleration will be so high that it means that it will fail. The terrain or the asset, it will fail. Okay. And here we have an example. This is a tailings dam. Okay, this is a dam. Here we have tailings. So with the analysis performed with InSAR, you could see that between the last image of December 2017 and the first image of January 18, there was an increase in the displacement. There, if you use another image, you wait for 12 days, for example, if you are working with a Sentinel one, you see it's even increasing more the displacement following the same velocity, but here there was a change of velocity. Before it was the displacement, the velocity of displacement was following this trend, and at this point, the velocity increased. Then you see it's even increasing more, but you can tell me, okay, maybe this is not just, this velocity is not constant. It seems that it's accelerating. Yeah, it was accelerating here. So what we did was like perform an inverse velocity analysis to see when the inverse of the velocity it's going to zero. It means infinite velocity. And we said, okay, if everything is going the same way, we estimate that this will fail the 3rd of March of 2018. And we calculated this on the 13th of February. Of course, if you have more images, you can do a better estimate. So we added another image, and we checked that the displacement was increasing even more. And it was still accelerating. So with this new image, 25th of February, we perform again the inverse velocity analysis, and we estimated that the failure date was not the 3rd of March, but the 5th. And then finally, it failed on the 9th of March. So this is one thing you can do with inverse velocity analysis. Of course, this is not a slope stability analysis. It's just a fast and first approach, as I said before, using InSAR data. Here you can see what I have shown now. we were performing an analysis the 8th of January, and we saw some deformations. 12 days later, we saw that the displacement increased. It was 1.5 centimeters. Yeah, then 1st of February, we saw it even increase more, and we could see that the velocity was increasing at this point, at late December, at the end of January, beginning of February. So you can mark this here. Okay, this area more or less experiencing displacement, but here the velocity is increasing. So watch out. And then 24 days later, the displacement was even bigger, and the velocity was not only increasing but accelerating. So you can, instead of placing increase of velocity, you can point out acceleration. So here you are saying, okay, this area is not only the velocity is not only increasing, but it's accelerating. And you perform this inverse velocity analysis that gives you a first approach. Okay, that's what we do with InSAR. And as I said before, managing the time series, the data that you get. But additionally, not using only InSAR, not using only radar images, but also using optical images. You can combine the results using optical images with the results from InSAR. And here, what we do especially is getting the humidity from tailing storage facilities, in which the content of water can change from one period to the other one. So with the multispectral analysis of the optical images, we are able to see how water bodies or water or humidity in general is changing from one place to another, and mix this with InSAR data and see if in some places where you had some displacements, also the water content has changed. And we do this using the optical images of a satellite Sentinel-2, which has an optical sensor, not a radar sensor, but an optical one. So you have optical images with several bands. So working with different bands, you can get these humidity products in which you can differentiate water bodies, and you can see the evolution of the water bodies over time, especially in areas where water can play an important role. So just to finish with some final comments. With InSAR, you can get displacements and rate, velocity of displacement with quite good precision, let's say millimetric precision. And you can get analysis at large, detailed, and side-scale analysis, which is a really powerful tool that can give you this different scale analysis. Where we always mention that InSAR is not. It's like it didn't appear to be the substitute of any other monitoring technique, but is a complement. You can perform large scale analysis or detailed analysis or side scale analysis, but at a certain time, I'm pretty sure you will need the help, the support of other monitoring techniques, because it can give you information about some areas where some techniques cannot bring light, but for example, in areas where I don't know very specific events are happening, other techniques can help you to better characterize the instability you are having there. And yeah, it's a remote technique, so you don't need installation or instrumentation of anything or the presence of staff, and you can get remote locations which are difficult to get access. As we said before, it can operate on day and night, and it doesn't matter if we have clouds or not. We will have probably more turbulences in the atmosphere, so we will need to do a better filter. Yeah, InSAR cannot always operate. If there's snow, if there's water, if you have increase of humidity or vegetation, or there are a lot of surface changes, all these things hinder the InSAR measurement, because you have a drop in the quality of the data, in the backscattering of the signal. So InSAR cannot be applied in some of these scenarios. And yeah, it's not very sensitive to north-south movements. As we saw before, we are getting images in ascending orbit. InSAR is looking to the east, so it's sensitive to the east-west movements, and in the ascending orbit it's looking to the west, so again is very sensitive to the line of sight, so to east-west movements, but to north-south movements it's not very sensitive. And if we have fast movements in small areas, maybe they cannot be visible in InSAR, because we can have the correlation. So finally, a combination of InSAR and multispectral analysis outputs may result in a good approach to prevent bearing failures, and of course with other techniques. So thank you very much for your time. I think it's just 12-30 minutes for questions, so I will not bother you more with this. Thank you.